Day 65 Notes, Advanced Algebra 2. Today we're going to learn a new technique to expand binomials, or in other words, to multiply several binomials in a row. Traditionally, when I see a binomial that needs to be squared, we might think that this is the same as x plus 1 times x plus 1. And we can multiply those two together by foiling to obtain a result of x squared plus 2x plus 1. X times x gives me the x squared. X times 1 gives me 1x. Another 1 times x gives me another 1x, so those combine to make 2x's total. And lastly, 1 times 1 is equal to 1. Our end result here is a trinomial, x squared plus 2x plus 1. When I see three of these multiplied together, however, x plus 1 times x plus 1 times x plus 1, the task becomes a little bit more difficult. Now, we might recognize that the product of two of these together is the same as what we found just a moment ago, x squared plus 2x plus 1, but that result needs to be multiplied by another binomial, x plus 1. And we learned a neat way to do this, or to complete this multiplication, in yesterday's notes. We can build a table, x squared, 2x, and 1 can be listed as a row, and x and 1 can be listed as a column. Then we can multiply each row by column here and find our result for this product. This leaves me with x cubed. This gives me 2x squared and x. Then 1x squared, 2x, and 1, which ultimately leaves me with the result x cubed plus 3x squared plus 3x plus 1. That's the result for x plus 1 cubed. Now, to complete x plus 1 to the fourth pattern, we'll try that once again. X plus 1 times itself 4 times in a row might look something like this. And you may recognize the product of these two pieces are the same. We should multiply x squared plus 2x plus 1 times x squared plus 2x plus 1. Each of these two trinomials is a product of the two binomials above it. And then off to the side, we might do some side work, this table calculation that would allow us to find a result. X squared, let me give myself a little bit more room. X squared, 2x, and 1 should be multiplied by x squared, 2x, and 1. So the first row comes from one of these trinomials. The column comes from the other trinomial. And we can set up the table to show our calculations here. X squared times x squared is x to the fourth. X squared times 2x is 2x to the third. 1 times x squared is x squared. Here we have 2x to the third, 4x squared, and 2x. And lastly, x squared times 1, 2x times 1, and 1 times 1. Remembering the pattern that's formed, these diagonals can add together. These diagonals can add together. And lastly, these diagonals can add together. That's a neat pattern that forms when we organize our work in standard form. And our end result here is x to the fourth plus 4x cubed plus one of these, 4 of these, and one of these. That makes 6x squared. Then 4x and 1. So the end result for this product is x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. Now, we've taken some shortcuts. We've saved some time by recognizing prior results. For example, the x plus 1 times x plus 1, we reused this calculation a couple different times. But there's a neat pattern that develops when we take a binomial, like x plus 1, or any other binomial for that matter, and raise it to a power, 2, 3, 4, or any power for that matter. What sort of patterns do you notice with each of these answers? Take a minute and look at each of these results and think of what you can see. For me, one of the first things that I noticed is that as we start getting bigger and bigger, I noticed that this x value here and this exponent tends to lead our answer of our polynomial. So here this is x to the 3rd power, this is x squared, and in each case that was our, oops, not that one, we should have this one highlighted. That's our leading coefficient of the result. And then from there, I notice that the exponent decreases by 1 every time until we get down here to the end where I have x to the 0 power. Did you happen to notice that too? Well, if you saw that pattern, that's really good. We will revisit that pattern at a later chapter, this idea of reducing our exponents in that fashion. That's what we call the binomial theorem. And that has a little bit to do with obtaining these results. But there's really more information that goes into that than what we're prepared to discuss. Now, in addition to that pattern that we find, students often notice that there's a pattern that forms with our coefficients. In this case, we started with a 1, we increased to 2, and went back down to 1. For our coefficients here, we went from 1 to 3 to 3 to 1, back down. And then in this example, we see 1, 4, 6, 4, and then 1. There's a pattern, there's a clear pattern that's starting to form where our coefficients start to increase and then they reduce at the same rate coming back down the other side. And you may have noticed that the first entry is always 1 and the last entry is always 1. Beyond that, you might see that this second value increased by 1 each time. So we went from 1 to 2, then 1 to 3, and then 1 to 4. You might guess that the next one is 1 to 5. And you would be correct. Actually, to find x plus 1 to the 5th power, we won't work through all of that, but that result is x to the 5th plus 5x to the 4th plus 10x cubed plus 10x squared plus 5x plus 1. And our exponents decrease by 1 every time again. And our coefficients start with 1 and jump to 5. Then we get a 10, and then back down to 5 and 1. If we look closely at the green highlighted marks here, these coefficients, there's a pattern that's formed, and it was identified by a mathematician by the name of Pascal. And these coefficients can be listed in an object, what's known as Pascal's Triangle. Let me show you what that looks like. Row 1 of Pascal's triangle starts with the number 1 all by itself. If I go on to row number 2, I'm going to add a 1 and a 1 at either end. For row number 3, this is where we start to see the patterns that form the coefficients, as we've seen up here. In fact, instead of calling this row 3, let's call this first one row 0. This second one is row 1, and this third we'll call row 2. And you'll see why in just a few moments. But row 2 we'll say is 1, 2, and then 1. Row 3 is 1, 3, 3, 1. I'm going to run out of room, so I'm going to move these over to the left just a little bit. Row 4 is going to be 1, 4, 6, 4, 1. And we saw that row 5 was 1, 5, 10, 10, 5, and 1. Can you tell what's forming the rest of this triangle? How are we going from row to row? Well, perhaps you've noticed that 2 adjacent numbers in any given row adds together to make the value directly below it. So back here in row 1, 1 and 1 are side by side. They're adjacent to one another. When added together, that produces the result 2. In the next row, I have 1 and 2 that are adjacent. Those two add together to make 3. 1 and 2 again add to make another 3. 1 and 3 add together to make 4. 3 and 1 add together to make 4. 3 and 3 makes 6. In the next row, 1 and 4 makes 5. 4 and 6 makes 10. 6 and 4 makes 10. 4 and 1 makes 5. Row 6 adds 1 at the beginning. 1 and 5 makes 6. 5 and 10 makes 15. 10 and 10 makes 20. 10 and 5 makes 15. 5 and 1 makes 6. And we finish out that row with 1. What I would like for you to do between now and tomorrow is fill this Pascal's triangle out for the next few rows. I'd like to see what the result you get by the time you get down to row 10. What are the entries going to be by the time you get down to row 10? Now, if you filled this out and you ran out of room working sideways, like I just did in this example, then please create this on a separate sheet of paper and bring that to class tomorrow. Create Pascal's triangle on a separate sheet of paper up to 10 rows. We've completed 6. I'd like to see you complete 10 on your own. Bring that to class tomorrow.